Okay, so good morning. We now know what is an inner product, a scalar product, and how to use that. And that is so, in particular, we know that that's the previous corollary, in any Euclidean space, we can get an orthonormal basis, or more generally. So Euclidean just means finite dimensional with an inner product. So the inner product provides you a way to measure things. So it gives you a norm and a way to calculate distances between two items, as the distance is defined as the norm of the difference of the two items, and so it also provides you an orthogonality concept. So out of that, we could prove that using that, we prove that out of any linearly independent family, we could build a family that was orthonormal. Each element would be orthogonal and also normalized. That was the Gram-Schmidt process. And so if we have a finite dimensional space, we know we can find a basis. And so the conclusion is that any Euclidean space has an orthonormal basis. So that was pretty important. Then let's see what we can do. Okay, so orthogonal subspaces. If E is a pre-Hilbert vector space of any dimension, so I remind you, just pre-Hilbertian space just means that it's a linear space with where we could define a correct inner product. Okay, so we know that we have a well-defined inner product on the space. Right, so we have first a definition, the orthogonal complement of a subspace. What is that? So it's going to be very naturally defined as, so you've got a subspace F, and it's going to be the complement subspace where you get that all the elements are orthogonal to every vector of the first subspace. Okay, so if you have a linear subspace E, its orthogonal complement will be denoted like this, with a small orthogonal sign at the top right of it, and it's going to be all the x's in E such that for every y in F, the scalar product between x and y is equal to 0. Okay, and very naturally, we get the following propositions. Given F and G two linear subspaces of E, then, well, first of all, the orthogonal complement is a linear subspace. Okay, that is pretty easy to show. How can we get that? So let's prove this first one. Okay, so you remember, to show that it's a subspace, we must prove that 0 of E belongs to that one. So let's see, why is that true? If we have for any x that belongs to F, we have that 0 of E inner product with x is of course equal to 0, so we can say that 0 belongs to F orthogonal. Okay, that's pretty clear. That's the first thing we need for a subspace. Second thing, we need the linearity property to be satisfied. So any let's say for any x in F, first let's start with that. Do we have that any linear combination of items in F orthogonal is still in F orthogonal? So we need y and z that belong to F orthogonal. We need lambda that belong to R, and we're going to try the linear combination of lambda y plus z. Okay, what does it do if we do the scalar product of this linear combination with x in F? So using linearity, I get lambda y x plus z x. And of course, as both y and z belong to F orthogonal, the two inner products that I've written here are equal to 0. 0 equals to 0 too, so the both things are equal to 0. If I can write equal to 0. So we have those two properties together that are giving us that F orthogonal is a linear space, a linear subspace of E. Okay, that's all right. If F is included in G, then G orthogonal is included in F orthogonal. All right, what do we need to do when we want to prove that two spaces, well, one space is included into another? We need to prove that for every item in G orthogonal, then it also belongs to the bigger one, okay? So that's what we need to prove, okay? So in order to, let me first erase what I have written for the previous one so that I've got a bit of space to do the proof. So let's do that. Okay, so let's start with this. So let's assume that let's take some x that belongs to G orthogonal. All right, what does it mean? It means that for any y that belongs to G, then I've got the inner product of x and y is equal to 0. Okay, and what do I get? And I want to prove that that x is also going to be orthogonal to any y or any z that belong to F. That's very simple. Then what do we have? So we get that. So we get that for any z that belong to F, that belong to F, of course, they also, so any z that belongs to F, of course, as F is included in G, that belongs to, belongs to, not, okay, that belongs to G. So what do we get? We get that Z with x is equal to 0, so that x belongs to F orthogonal. Okay, that's it. That's what we needed to prove. We needed to prove that if we started with any item from G orthogonal, in the end we proved that it also belong to F orthogonal. All right. Okay. So think of it like so maybe you've got, so what was it? We had a set F that was included in a bigger set G. What's happening is that the complement is going to be outside. Okay, so you see that the outside of F is going to be bigger than the outside of G. Okay, so that seems pretty intuitive when you consider that kind of drawing, which is really just a very rough representation just to help you sort of visualize what's happening. It's really clear that the G complement, the orthogonal complement of G, is going to be smaller than the orthogonal complement of F. Okay, right? Because, well, assume that this is content in a whole space E, then of course the outside of the smallest one is bigger than the outside of the biggest one. Okay, that's one way to say that. All right, next we get this proposition. Given a linear subspace F in E and a vector U in E, then U belongs to the orthogonal of F if and only if U is orthogonal to elements of any basis of F. Okay, all right, so that's also pretty direct to prove. So what do we have? First of all, so we've got an if and only if, all right? So when you have an if and only if, you know that it should, it means that you've got an equivalence. So we need to prove this equivalence. Okay, let's first of all maybe let's erase the side. Okay, so we want to prove this proposition. All right, so which says U belongs to F orthogonal if and only if U is orthogonal to any basis of F. Okay, so as you know, when we've got an equivalence, we have the two directions to prove. Okay, so well, first direction, the direct implication is absolutely direct. If U belongs to F, it just means that for any x in F, U is orthogonal to X, and in particular, if you take any basis of F, it's going to be orthogonal to it. Right, so that's absolutely trivial for that sense. The indirect implication is a bit, we have to write what's happening. So what is the assumption here? We assume that U is orthogonal to any basis of, sorry, U, I was writing, U is orthogonal to any basis. So let's give a name, EI. So we are in a Euclidean space, so we know that it's I is equal to 1 to n. We have well, we know we have a basis, so we have a finite number of elements in our case, right? And so we know that, let me try to erase that ugly stuff here. Okay, so for any x then that belongs to F, if I've got a basis of F, I know that x can be written that uniquely written with respect to any of its bases as x1 e1 plus x2 e2 plus xn en. Okay, and so if now I'm doing the inner product of u with x, it's just the inner product of x1 e1 plus x2 e2 plus xn en with u, and so using linearity is just going to be, well, x1 e1 u plus x2 e2 u, etc., plus xn en u. And if I've got, by assumption, that u is orthogonal to any elements of any basis, I know that this is 0, this is 0, this is 0, so in the end it's equal to 0. And so that for any x, I really have that for any x in F, I really have that x scalar product with u is equal to 0. So in the end, it just means that u belongs to F orthogonal. Okay, so and that proves proposition 6. Let's give some very simple examples of orthogonal complement. Right, so let's say you've got an inner product space E. Okay, what's the orthogonal complement of the 0 of E? Well, it's going to be the items that are all orthogonal to 0, but we know that 0 inner product with any x is equal to 0. Okay, we've already seen that several times. So for all x that belong to E, so the 0 orthogonal is actually E itself. Right, that one was pretty simple. And same way, you can prove that the E orthogonal is going to be equal to the 0 element. That's one element that is orthogonal to any of others. Another very simple example in R3. Okay, let's denote F is equal to the span of one vector A, B, C in R3. Okay, what is the orthogonal complement of F? Okay, answer in the next video, but try to do it by yourself.